First one is about the cohomology of Grassmannian. This is corrected by Professor Panov-san. I wrote the cohomology of Grassmannian is isomorphic to this polynomial ring divided by ideal, but I had to consider just the invariant part of polynomial ring. What this means? Sm is just the permutation of first m variables, and Sn is the last n variables. And the second mistake was pointed by John Beck-san. Here, I wrote 2, but it should be 0 because this and this are conflicted. Okay, I will continue to give some open problem.
And symmetric group should you write S lower.
Yes. Sorry.
Yeah. SM
Yes, SM. I think now the blackboard is free from mistakes. Okay. So first, here is an example for AJI. If we take W as an element of S4, like this, then this permutation can be decomposed into simple transposition as this. Then we can explicitly give this matrix by this rule. For example, this number was given by comparing 2 and 3, and 2 and 3 has distance 1. Then we put 1 here. For example, here 1 and 4 has distance 0, so we put minus 2 here. Anyway, an element of symmetric group determines some Bott tower.
You mean K must be less than N?
K must be this. No. N factorial. Yes, the longest element. So 1, 2, 3, 4, 4, 3, 2, 1 has 4 factorial disorder. So we need 4 factorial simple transposition. Not 4 factorial. No, 3 factorial. 3 factorial. Sorry. No, not factorial. 1 plus 3, 2 plus 3. Sorry. 1 plus 3.
So here I and J is less than N.
Yes. I and J listen.
Then double.
I and J. No. I and J. No. I and J is not restricted to.
I and J is
less than K.
So now the part tower is not H state, N state part tower, right?
Yes, K stage.
K state.
So and the open problem. Before stating open problem, we need some more definition. For lambda in browser one, we define W lambda in N as sorry. So x W one lambda one x W three x k lambda k. This means, for example, if we take lambdas 1, 0, 0, 0, then W to the lambda becomes as 2, or if we take 0, 0, 0, 1, then becomes S2, S2 reduced to just identity.
So lambda k's power is just a iteration of SWK lambda k times. You said SW to the lambda
Yes.
1, SW1 to the lambda 1's power, right?
Yes.
So that means, what do you mean by lambda? Oh, lambda is just 0 or 1?
0 or 1, yes. So this chooses some subsequence from the sequence for W.
Here, ij is from 1 to 4. Ij.
Yes, in this example,
But the number of k is different.
number
At
of
most,
k
at
is-
most n minus 1 plus n minus 2 plus
Yes.
1 plus n minus 1. 1 of 2 n minus 1. So 2 to the n minus 2 to the n minus 1.
One sub index W sub j sub W I, right?
Yes,
That's still ij, right?
yes.
That's
Wij,
sub index k, ij k, right?
okay, so to make it clear, I and j is 1 to k. This is, and W I is within. Is it correct?
So the maximum
No.
commutation should be
Minus 2.
So the matrix is the k by k matrix.
Yes, K by K matrix.
from 1
So
to
it's
n.
just 4.
1, 2.
You are adding from 1 to n minus 1.
N minus 1.
So 2 to the n minus 1, right?
N minus 1?
Yeah.
N? Yes. Yes, I have to re-enter elementary school.
So here you need the S4 case, right? The k is the 6.
K is at most 6. But
6 slash
But I think if omega is given,
yes,
then this k is fixed. And then you define aij for
Yes.
each depending,
for given omega.
for
Yes.
even omega. So aij is depending on omega.
So that's what I want to ask. So
Yes.
if you have W,
Mhm.
and there are several expressions of W.
yes.
Then
Then you have another bota. Yes, so
Not
So-
only w, but it's this expression.
yes, expression. So, sorry, I have to mention. But the solution is not affected by the reduced expression. Okay, so then. theorem by Samuelson and or one or Williams is that the structure constant is same. Can be computed by using Bott-Samuelson variety, but complicated way. Goes to the So, what is LU? LU consists of lambdas which satisfies this condition. W to the lambda is reduced decomposition of U. For example, so this is a little complicated, so I think example helps. And so in this example, for example, if you take U as S2, then LU is 1000 and 0001, because at the first position and the fourth position we can find this 2. So what are, okay, and what is the reduced decomposition? Reduced decomposition is a minimal way to decompose some element of symmetric group into the simple transposition. No redundant relation. For example, if V is S3 S1, then V is here. So, since we know how to compute this monomial, this product of monomials using ideal relation, so we can get the structure constant this way. So this was the observation by Bott and Samuelson, and later, very recently, they did, in a sense, renewed the theory of Bott Samuelson. And it is mysterious. There is some mystery. Since Bott tower was first defined by, like, that just I wrote as a definition of Bott-Samuelson variety, but now someone stole the name of Samuelson from bot Samuelson. Then now we call it just bot tower.
I think who is responsible for that? Passion thinks good.
There was some problem between them.
They were first named it as a platform. It's like a Stanley
Anyway, this solves the problem of structure constant. But there are many cancellation by just using standard way to compute this. So, second question is find manifestly positive way algorithm to compute left-hand side. Manifestly positive means can you prove this product is always positive from the computation in bot tower? This number should be positive because this corresponds to structure constant or tensor multiplicity or something. So this structure constant is positive, but if you compute by standard way in the homology computation of bot tower, then you'll have a lot of cancellations. So we don't know why this number is positive from this expression. So if you can prove this gives positive number, then you solve the open problem in Schubert calculus.
So here, if you fix K first and then you equation.
Yes, we have to fix all of three. Then
But I don't know why you choose in S the symmetrical field.
Mhm.
You just use the sequence. So
yes. So there is a correspondence or inclusion Young diagram into a symmetric group. It is just easy, but a little complicated. For example, this this corresponds to okay, so sorry. I have some time to 1, 2, 3, 4. Okay, more easy. This corresponds to 1, 2, 3, 4. So distance between here, the number of boxes corresponds to the distance between the upper and lower number. Okay, but this correspondence is very well known. You can find it anywhere. So please let me go further. Okay. now we will discuss more general setting of both general plug variety, and also we consider the torus action of it. And this simplifies many things. Apparently, considering adding some more structure makes the problem difficult, but in this case, considering torus action makes problem much simpler, as is often the case with Toric topology. But I use from now on I use section. We will need a lot of notations, so please be patient. Let G be connected complex ring group. And if you are not comfortable with general E groups, then you can no complex.
Oh, complex.
And B Borel subgroup, which is a maximal solvable subgroup of G, just upper triangular here. And maximal compact torus. Compact torus diagonal. And KAIST dual Lie algebra for maximal torus. So this is just Rn spanned by E1 to En. Standard basis vector. And wait.
Not the diagonal matrix,
That,
you want times this matrix.
yes. Because there is inclusion. Then
Yes. That's about it.
yes. Diagonal. Okay. I see one. Diagonal. Thank you. And beta be positive good. Reflections, not reflections. Just vector given by T じゃないですね。はい。And simple roots. Are denoted by alpha t I plus 1 minus t I. And W file group in this case just symmetric group of n variables. And S beta in W reflection data defines some hyperplane, so we can consider reflection. Then W can be considered as a finite group generated by simple reflections corresponding to simple root. Satisfying some relations. For example, 2 times S alpha I is just identity because if you reflect twice, then you don't do anything.
You think any is complex Lie, but not simple Lie? Not simple.
I think the word Lie group means
yes.
reductive algebraic group over C.
Okay. Anyway, any.
Okay, any.
Usually.
Not reflective.
W is S alpha 1 or S alpha I?
Sorry, it's alpha 1. It's alpha 1 to, since there are n minus 1 simple reflections in the case of GLN. Okay, so I wanted to give an example, but example how to consider this root system clearly, but I don't think I have time, so skip. Okay, fundamental theorem. And I forgot to give a most important definition. Since B acts right multiplication on G, but since B acts by right multiplication on G, we can consider the homogeneous space G over B, and this is called Frag variety. In the case of GLN, Frag variety is just FLN defined to be the space of sequences of linear spaces. This is a kind of generalization for Grassmannian, because for the Grassmannian we choose just one V subspace, but instead we consider all the sequences. And fundamental theorem by Schubert states that G over B Frag variety has a self-decomposition given by double orbit, left and right orbit, indexed by the elements of while loops. So as a corollary, we can define Schubert variety omega W as the closure of those cells. Schubert variety.
I'm sorry.
What means DW? What means DWB?
BWB means, okay, W can be considered as an element of G because it is a quotient, but we multiply B from the right, then we can choose any representative for W. And so this is just a point, and we consider its B orbit from the right action. Right, not left action. So this is the definition of Schubert variety, and corollary of the theorem by Schubert, immediate corollary is H star should probably Z is just generated by these classes. But just this isomorphism is Z module isomorphism. So the problem here is again how to compute the cup product of two Schubert varieties. Here again, this constant is called structure constant. The problem is algorithm for structure constant. This is the main problem in Schubert calculus. And since we defined Schubert variety as a B orbit, so this is Schubert variety is T stable. Here T acts on Grassmannian by the left multiplication.
What are the Schubert varieties when you have G as a GLNC?
It's defined by, yes. So
like similarly as in the
Yes,
Grassmannian
condition.
case?
Condition.
I see.
Yes.
So generalizing this Schubert,
Yes.
Schubert cells.
Yes. Since this variety is T stable by the function of maximal torus from the left, yes, because B includes T.
B includes T, right? Yeah. Okay.
So this gives also equivariant, an element of equivariant convolution. This class can be considered as H T. So we can consider the same problem in the equivariant setting. Here, this structure constant is no longer just a positive number, but an element of BT polynomial. Because the coefficient for T equivalent cohomology is, since the cohomology of equivalent cohomology of point what we want to know is an algorithm for structure constant in equivariant cohomology. This program is called equivariant Schubert calculus.
But manifold, you still have
Yes.
similar
Yes.
phenomenon like this, right?
Yes, yes. Okay. So, Ima, in the case of dot manifold, again, this submanifold defined earlier is T stable and corresponds to just monomial, and now homology is coefficient divided by x I square is equal to some lambda I x I plus a I j x a j I But this part is exactly the same as before, but we have to add some equivariant part here. And lambda is in the cohomology of BT. So in this setting, we can again ask the same problem as before. Find an algorithm for the product of this subvariety. And there is equivariant version of Bott-Samuelson theory, and it also proves the equivariance between some Bott calculation in Bott tower and calculation of Schubert structure constant.
I understand this is BT algebra or?
As BT algebra.
As a ring, they are just base ring of
Yes,
cube,
yes.
right? So the same question is still open.
Yes, because this is this includes equivalent case includes the ordinary case. Just we put t to 0 and we obtain ordinary. And what is positivity here is so the structure constant is apparently here, but actually structure constant is in positive coefficient if you write this polynomial by the generators of simple roots. If you rewritten structure constant as polynomial of simple roots, then the coefficient must be positive.
So here, lambda I will be 2.
Yes, B2. Okay, so in the ordinary case, we know the ring structure for this cohomology as described as polynomial ring divided by some ideal. So what is such representation for the equivariant case? Which is called Borel representation of So I will give two descriptions of equivariant cohomology. The first one is Borel representation, which corresponds to the polynomial representation in ordinary case. So first, K be the maximal compact subgroup of G. For example, if G is general linear group, then we can take K as SUN. And then Iwasawa decomposition gives isomorphism, diffeomorphism. Sorry, this UN. Sorry. This is the equivariant diffeo given by Iwasawa decomposition. So, especially we can consider the equivariant cohomology of K over T, compact presentation of Bragg variety, instead of the original T equivariant cohomology of Bragg variety. Braille construction for compact form of Bragg variety can be written as the product diagram as follows. This is product diagram. Just the definition of Braille construction. And if you add let R be a integer ring of integers with some primes inverted. And what primes are inverted? So, or if you don't want this kind of thing, then you can just take this thing as Q. Your PG is torsion prime. And it is completely known. And for example, for classical type, for GLN, we don't need any P. For SO case, type B of type D, we just need 2. Prime 2 has to be inverted. This corresponds to the result of Fukuoka-san 2 days ago. And
so what is the torsion prime?
Torsion prime is prime. So torsion prime is, if you consider the homology of G, then rational cohomology is very easy, but there are some torsions. So so torsion prime is where the torsion sits.
You mean this?
If you have 2 torsions, then you.
Oh, you mean the number, degrees?
No. Primes. If you have 2 torsions in the homology of G.
So the collection of all.
Yes.
I see.
All primes.
Okay. So this is a prime number.
Prime. Yes.
Number, right?
Prime numbers.
Yeah.
Torsion prime numbers.
So they are prime numbers.
Yes. So for example, if G is GLN, then P G is empty. For P S O N, you need 2 to be inverted. So if we invert some primes, then you'll have a nice presentation of the cohomology of classifying space is R coefficient. It is just invariant part of the cohomology of PD. So you can compute this Provak space using Eilenberg-Muller spectral sequence, as is like moment angle complex. We can use Eilenberg-Muller type spectral sequence because this part is just free resolution with height 2. Okay, so the diagram induces diagram of algebras. But now this is just invariant, and this map becomes so using Eilenberg-Muller spectral sequence. Describes the cohomology of Provak, what we want to know. As the torsion over this in here. Of this is just polynomial ring. First one is corresponding to the left BT tensor by right hand side BT divided by relations given by this form, and where f is invariant polynomial. So this means for example, in the case of GL and you get because we don't need to invert any prime, we can take the coefficient as T1 Tn, C1 Cn divided by elementary symmetric functions of T tends out 1 minus elementary symmetric functions of Z. If you don't need tensor. So this recovers the result of Fukuoka-san. And in addition, we can use explicit connection with Fukuoka-san's result. This T generator corresponds to X generator in Fukuoka-san's notation, and Z variables corresponds to tau variables in Fukuoka-san's notation. And okay. So if you take type D or type C type D, then we can explicitly write this kind of correspondence to Fukuoka-san's result. And that what I wanted to explain by two descriptions, but I don't think I have time. Okay, so I just give some headlines. Okay, so the other description is by GKM graph. GKM description or graph equivariant cohomology. Then, so this is graph cohomology for some combinatorially defined graph. And Fukuoka-san told that this graph cohomology is exactly equivalent to the cohomology of Bragg varieties. And we can describe the explicit connection between this polynomial representation and GKM description. Explicit translation. Between the two. And there are both advantages and disadvantages for each description. For example, this description is very convenient because we don't need a lot of polynomials, list of polynomials right here. This is convenient. But here we have to consider ideal. But here we don't need to consider ideal. So for question 2, this is ideal place to consider question 2. And actually, we can solve question 2 here. And for question 1, how to find polynomial representative here, we can give some combinatorial condition for the representative in here. Then, using this explicit translation, we can find a representative for the polynomial representing Schubert class. So this answers this gives the answers to the question 1. So we now have both answer for question 1 and question 2. Then what is remaining is do actual computation for all the cases, and it can be done using, but we need to use computer. I stop here.